Yes. Okay, everybody. Thanks for coming. Sorry for the late start. So today I'm going to talk about an assortment of things that we weren't able to cover the last time. So that's going to be dequantization, which is something that you guys had to implement for the flow assignment. So I'm going to talk more about that and how that is related to variational inference. And then I'm going to go on and talk a bit more about VAEs. It's just a completely separate topic, to be honest. This is going to be hierarchical VAEs, which are the types of VAEs that achieve the best results right now. These are state-of-the-art VAEs in terms of density estimation performance. And then I'm going to go on and talk about compression. So when we do compression with VAEs, we need to have an algorithm that turns symbols into binary strings. So the sort of latest and greatest such algorithm is called ANS, or Asymmetric Numeral Systems. So I'll talk about how that works. And then that's going to wrap it up for latent variable models. And then Aravind is going to talk about GANs, which are the next class of generative models. Yeah. I can't do that while I'm lecturing. Okay. Okay. Yeah, just the latest ones on Google Slides should be. Yep. Okay. Oops. How do you actually advance slides? Okay. All right, so when we train flows, flows are density models, which means that they naturally fit to continuous data. But the kinds of data that you saw in your assignment, well, that's not exactly continuous data. So when we work with images, that's really, well, each coordinate of an image is a number from 0 through 255. Raised to the power d, where d is the dimension of the data. So something like 784 for MNIST or 3000 something for CFAR. So this is discrete data, which means that if you try to fit the best density model you can to it, you're going to get a negative bits per dimension. So I think some of you might have actually seen this. You have this loss that goes negative. And that kind of doesn't make any sense because compression is about bits, right? You can't have negative bits. You can't store a file with negative bits on your hard drive. It just doesn't make any sense. And the reason it doesn't make sense, or the reason this happens, is because if you have discrete data in this continuous space, that's going to be a set with zero mass, or that's going to be a zero volume set. So that's why it's not really, that's why density models don't really work with them. So to deal with this, the way to solve this problem is to give that set some mass. The way you give it some mass, or the way you give it some volume, some non-zero volume, is by adding noise. So this is how it works. So here, we're working with this density model, P model. That's what this is here. So P model is your flow model. You know how that works. And so what we tell you to do, or what most people do, is they add uniform noise to the data. In other words, they draw this uniform random variable from 0 to 1. So keep in mind that this 0 to 1 is somewhat arbitrary, but it is very suited for data which is in this form, because the spacings of all the points from 0 to 255 are exactly 1 apart. So that's why it makes sense to add uniform noise from 0 to 1. But that's what you do. And that's what we define this distribution to be. So this p data with a small p is exactly given by sampling one point from the data set and adding noise. Yes?
So can you remind me why negative bits per dimension happens?
Yeah, so
even if it has zero mass, the signal will like non-negative.
okay, so entropy is, yeah, exactly. So entropy is log volume. So if volume is less than 1, it's going to be negative. Yeah, and so that's why we have to add enough volume to make it bigger than 1. So that's that. And so this is the objective that we ask you to maximize if you use uniform dequantization. Yes?
So like for the homework, because our like channel bits were only like 0, 1, 2, 3, even adding noise uniformly from 0 to 1 would pretty much add like 25% of the signal as noise. Right. So is there, obviously that effect gets decreased the more, if you have actually 256 like range for X, but is there a better way to do it, or one that might be better suited for like quantized like channel
Yeah,
bits?
that's the next slide. Okay, so just talking about uniform dequantization here. So what we ask you to do is, well, sample data from Y, which means sample a point from the data set X and then add uniform noise to it. So this, and then maximize the log likelihood of that point. So that's what this says. This is sample a data point from the data set. And then this integral, well, that's the expectation over the noise. So it just says sample one point from the noise distribution. And then you maximize the log likelihood, the log density of your density model, the flow, under this point, the dequantized point. So this, if you were to think about this in PyTorch or TensorFlow, what this equation says is sample data and add noise to it, and then take a gradient step. Does everybody understand why this equation says that? Okay. And now, why is this a good idea? Well, the reason it's a good idea is that if you apply Jensen's inequality, so Jensen's inequality says to take this log and this integral and swap them. So if you apply that, then this is a lower bound to this equation. And what is this equation? Well, this is just the average log likelihood of data sampled from the data set. But now, instead of being the average log density, it's actually a log of a probability mass function. Okay, so what is that probability mass function? So here, I claim this defines a probability mass function over X. So the reason it defines a probability mass function over X is that what this says is it integrates a density function over some cube. The instant you integrate a density function, you turn it into a probability mass function, right? So if you were to take this and sum it over all X, so over all discrete X, you would get 1, because that's what probability mass functions do. And also all of these numbers for all X, this is bigger than or equal to 0, because it's a probability mass function. In other words, this is a lower bound on the expected log likelihood of a certain probability mass function. Or if you flip it around, it says that the negative of this is an upper bound on the negative log likelihood of a probability mass function. And those must be non-negative, right? So that's why this fixes the issue. Okay, does it make sense why we want to do this and why this fixes the issue of negative bits, negative compression rates? It's because we've turned the density model into a probability mass function, and we're optimizing a bound on its performance. Okay.
So what's the difference? So you just change the small p to big P, right?
Yeah, that's right. But we define big P as the integral under this set, under this hypercube of the flow, right? And so that's actually a very difficult object to work with. This integral already here, over this set, that's already a very high dimensional set. So this is a high dimensional integral. So if you just look at this, if we ask you to just optimize that objective, that's already intractable. Because you have this flow model, and we're asking you to average over points inside this d-dimensional hypercube. So that's really hard. But the point is that if you instead consider adding uniform noise, then it turns out that's a variational bound. It's a way of approximating this integral. Okay, so that's what that does. But let's think for a second whether or not this is actually a good idea. So certainly it solves the problem of negative compression rates. But it's actually quite a difficult thing for neural nets to do. So if we imagine a density model, so over the real line, so here's one-dimensional data, and here's our density model like this. So that's your one-dimensional flow, or that's the density represented by it. If this is the point x, what this says is that what we really want to do is maximize this area. That's what the second line says. But what this variational approximation says, actually, is to maximize the density for all points inside this interval. So really what it's trying to do is make the density large for this entire set here. But in fact, if we want to make this integral large, actually all we have to do is make the density large at some points. We don't need to make the density large at all points inside this hypercube, right? And a hypercube is actually a very unnatural object for neural nets to work with. There's no reason at all why the flow likelihood surface should abruptly assign high density to just the cube and then low density right outside it. That's a very weird thing. So the natural question to ask is whether or not we can do better. And we can. So the thing to recognize is that we can do variational inference. So instead of this uniform noise distribution, we can learn a noise distribution. And the way it works is like this. So this is an application of variational inference. So this here, P model, is the integrated density. This is the likelihood of which we wish to maximize. And it's intractable. So we introduce some variational distribution, some approximate posterior, if you wish, Q. And now following the same exercise, you apply Jensen's inequality. So this log goes there. This expectation goes there. And we end up with this thing, which is, well, what you do is you sample data from a data distribution, then you sample noise from the approximate, from the dequantizer Q, that's what it is, and you maximize this objective. So the first thing to notice is that in the case when Q is uniform, so Q of u given x is always 1, this is identical to the previous slide. But in this case, you can define Q to be your favorite kind of variational family. It could even be a flow. And if you jointly maximize this objective over the flow parameters and as well as the dequantizer parameters, then what this ends up doing is it learns dequantization noise, which is easy for the model to fit. Right? This dequantizer is being optimized to maximize the model density. So it's actually trying to help the model. Does that make sense? So instead of saying, let's maximize the density over all points in this interval, what Q will do instead is try to find points in the interval for which it's easy for the model to maximize. So that's pretty cool. And it has a nice consequence, which is that if you train a flow model, yes?
How do you train these two things jointly or at the same time? Or?
Yeah, so the question was, how do you train these things jointly? Well, it's just like a VAE. So Q is going to be some approximate posterior, which you define to be reparameterizable. So you will take this thing, so you'll define Q of u given x, or sampling u, like this, is the same thing as sampling epsilon from some noise distribution, P of z, just like a VAE. And we define u to be Q of epsilon x, just like that. So it's just like an approximate posterior in a VAE.
I guess what I meant was, how do you know like how long to train Q versus P? Is this just something you empirically figure out?
Yeah, that's an empirical thing, though the same point actually applies to VAEs. Like, how do you know how long to train the approximate posterior of a VAE versus the decoder and so on? And so by far the easiest or most dominant way of doing this is to just train them jointly.
So like one example at a time to each or something, or what is?
Yeah. So what you do is you sample some x from the data, and then now you can take a gradient of this objective with respect to both the parameters of Q and P. and then you just take a gradient step on them together, thinking of them as one large parameter vector, and you continue. It's just like a VAE. Yes?
What stops the U from basically collapsing into like a
Yeah.
spike?
Okay, so the question was, what stops you from collapsing onto a spike? And that's a very good point, because that's what if that were to happen, then it's like we weren't dequantizing at all. So that would be weird if that happened. So why doesn't that happen? Well, the reason it doesn't happen is because of this term on the bottom. So this term on the bottom says, maximize the entropy of Q. Right? So the term on the top says, make the noise easy to fit. And the term on the bottom says, make the noise noisy. And that's why it doesn't collapse. Cool. Okay.
I have a question.
Yeah.
In the previous slide, previous to this, it's the small p is the lower bound for the big P, right?
Yes.
Then in the next slide, you derive the big P's lower bound.
No, it's an upper bound.
In the lower bound for the big P, right? So here is the upper bound for the small p. Derive the lower bound for the big P.
Let's see. It's, yeah,
Yeah.
that's right.
Bigger than this.
No, it's smaller.
Yeah.
But now it's not uniform, right? We're using this variation.
But this is a big P.
Yeah, just like flip the whole thing with your brain.
So this is inside. So the big P is the biggest, right?
The big P is the biggest. Yeah. Yeah,
Sequence shown because there's three, and the two inequalities shown do not determine
Yeah,
the sequence among the three.
yeah, I mean that.
I'm not totally sure if I understand the question.
Small p here is smaller than big P
Yeah.
on this
Yeah.
slide, and
Yeah.
big P on the next slide is
This is
Bigger than
bigger
Then-
than another something.
bigger than small p. Isn't that what we wanted?
but don't we want the two big P's to be comparable also in some way?
I really don't understand the question, actually.
I think they're going to compare like the expression on the left here
Yeah.
with the expression on the right on the next slide.
Oh, okay. So the expression on the left here, let's see.
That's the one where you added uniform noise, right?
Yeah, this expression on the left actually doesn't exist in the expression on the right, or in this slide, because that's uniform dequantization. And this is, the whole point here is that that's not uniform dequantization. Right, so this expression here on the left says sample data from the data set and then add uniform noise. So that never happens in variational dequantization. In variational dequantization, you sample data here, and you add noise drawn from the dequantizer. Not uniform noise. I hope that cleared it up. Okay, cool. All right, so why is this a good idea? So, or why do this over, yes? Yeah,
This is kind of a different question, but say,
Sure.
say we're not thinking about our discrete systems like images, but a case where we have like honest to God classes.
yeah, yeah.
Then how does that impact our inference on the Qs? Like if if I have two different values, one is much more present than the other in my data, what would my model want to do with the Qs? Like would it collapse around one and be flatter on the other? Or?
So I think that question doesn't have anything to do with dequantization, at least if I'm understanding you correctly. That's a problem even in discrete models.
Yeah, no, I'm not
right.
saying, I'm not like trying to criticize. I'm just
No.
saying, yeah, I'm just
But like, is it specific to dequantization, or is it is it a problem
quantization do in that situation?
if there's class imbalance?
Yeah, like just, if it's 100 to 1 or something.
Right. Well, one answer is that because this is variational inference, there's always a true posterior. So you can always actually infer the noise. It's intractable. And so in the case that you get a true posterior, then really you're maximizing the likelihood of a discrete model. Right? Because when you have a true posterior, the variational bound is tight, and it agrees with integrating out.
Are you assuming you have you have a model of the true noise? I mean, like, I give you observations of discrete data.
Yeah, yeah.
You are introducing this noise because you want to look at a continuous model.
Right.
So, in what sense are you saying this is a true posterior?
It's a true posterior in the sense that when you plug it into the variational lower bound, the value you get is that of integrating the density over all those sets. So there's actually no noise. The noise is fake. The noise is a tool for computing integrals. So that, well, that converts the question to what happens to the class imbalance problem for discrete data, or for discrete models. And there, well, I don't know what the answer is. If maximum likelihood works, then it should figure out the right fractions. It should match the fractions in the data set. Yeah. Yeah.
Can you please go to the next slide? So in this case, let's say we were to, like, so basically what we're maximizing is the expectation of, the log of,
Yeah.
density plus the entropy of Q.
Yep.
If we were to completely ignore the entropy, we would get a spike and we
Yeah.
would basically collapse to a situation without any
That's right.
quantization at all.
Yeah.
And if we were to give infinite amount of weight to Q, then we
Yeah.
would end up with a uniform distribution.
That's right.
Versus uniform quantization. So this
Yeah.
seems to be in the middle.
Yeah.
Is there a nice way to basically trade off between how much weight we are putting on the entropy and on the model?
Yeah.
Like if we were to add lambda in there,
Right.
I
Right.
can see how it would fit into.
Right. Yeah. So the question was, what happens if we weight the entropy of Q versus maximizing the log density of P? And the question is, I think, the same question of if you're training a VAE, how do you weight the KL term of the VAE, which matches the approximate posterior to the prior, versus the autoencoding term, which tries to autoencode as much as possible? And the answer is yes, you can weight the two things. But then the problem becomes that weighted objective is not necessarily a code length. It's not necessarily a bound on, on the marginal likelihood. And so I think that's sort of the best thing that's the best answer I know of. In practice, it can actually be useful to weight the two terms for the sake of better optimization. So it turns out that sometimes it's actually very hard to optimize this variational bound just by itself without weighting the terms, even though that is actually the objective you want to optimize. So what you do in practice is you sort of weight the objectives and change the weights online while training. But it's all for the sake of getting a better original variational bound, a better unmodified variational bound. So that's kind of how it is. I agree that it would be kind of nice if you could modify the weights, but it's not exactly clear what that means, other than helping optimization. Okay. Cool. Okay, so what does this buy you over uniform dequantization? Well, the first thing it does is that if you try this on a flow model on CFAR, so this line here is the test performance of a model with uniform dequantization. This is the test performance of a model with variational dequantization, which is actually another flow. And you can see that you do better. Okay, that's fine. That makes sense because it's a tighter variational bound. But I think what's a bit more interesting is looking at the train test gaps. So for uniform dequantization, you see this is the train test gap here. So that's about 0.06 bits per dim. And if you look at variational dequantization, this is the train test gap. It's 3 times less. So what this says is that this is sort of some evidence for the fact that learning dequantization noise, which is easier for the model to fit, is a good thing. Because that, if it's easier for the model to fit, then that means that there's a chance that the model will generalize better. Yes?
So if we can just add this like beneficial noise to our model to make it easier for it to learn
Yeah.
the true density, why don't we just like do this all the time?
You should. All right. Cool. Okay, so that was dequantization. Hopefully that maybe cleared up some stuff on your flow homework. All right, now I'm going to switch gears and talk a bit about VAEs. Oops.
Does this suggest that we should do it for continuous data? Is that the implication? Of why
No.
we do it all the time?
I don't think you should do it for continuous data. I don't think it really makes sense for continuous data.
Don't all these things go through all these equations?
Maybe, but the purpose of this dequantization stuff is to maximize the log likelihood of a probability mass function, which is defined implicitly by the density. So the density implicitly defines a probability mass by integrating over intervals or boxes. And if that's a probability mass function, then it doesn't really make sense to fit that to continuous data anymore. Unless you wish to quantize your continuous data. But then why not just quantize it and then do this? Which is the same thing. Yeah, this is sort of specialized to the case where you wish to fit density models to data which is naturally assigned to integrating out regions of space. Did that answer the question, or?
I'll have to think about it some more.
Okay.
That's all later.
Okay. Yep. Okay, so last time we were talking about VAEs. There are a bunch of things you could do to VAEs to make them really good, like really powerful approximate posteriors, really powerful priors, so on. There's some nice VAEs that do this. You can also make the decoders more powerful. But there's another, well, I don't want to say, this is not an orthogonal design choice, but this is another design choice that may go into designing a VAE, which is to design it to have some kind of hierarchical structure. Okay, so what does hierarchical mean? Well, if you look at this, this is the base net corresponding to a VAE, a standard VAE. You have some latent variable z, and you sample from it, then you get x. So that's pretty simple. And this is the joint probability of the data in the latent variable. So a very natural thing to do is to have a chain of latent variables. So here we have latent variables arranged in this Markov chain fashion. Here we have latent variables that are arranged in some kind of autoregressive fashion. But the point is that it doesn't really matter how you arrange them. The point is that there's just more latent variables. And so for all of these models, this is what the joint likelihood looks like. It's, well, you just plug it in, and this is what you get. This is just straight from the base net. So why might you want to do this? Well, one reason why you want to do this is, let's say you're working with a standard VAE, where P of z is a Gaussian, right, just a standard normal. And P of x given z is your usual thing, so like a conditional factorized Gaussian. And that VAE is going to have some kind of modeling capacity. And so before, we were saying that there are a couple ways to, or many ways to increase the modeling capacity of VAE. One is to, let's say, make this distribution more expressive, make it a pixel CNN or something like that. Another is to make the approximate posterior more expressive. But another one is to make the prior more expressive. So instead of having it be a standard normal, you could choose it to be a flow model, or you could choose it to be an autoregressive model. But there's another choice you can make, which is to make it another VAE. So that's kind of what's going on over here. So here, that's like a VAE model for Z1. And here, these 2 points, or these 2 variables, that's like another VAE for the prior of Z1, and so on. So that's kind of the design philosophy here, that by introducing more latent variables, you make the distributions at each part even more powerful. That gives you more modeling capacity. OK, so how do you train with multiple latent variables? So this might seem like a very complicated beast, but in reality, you just apply the same formula as before. So the way to do this is you treat all the latent variables. So here you have all these crazy complicated latent variables in some weird autoregressive-like structure. Well, what you do is you just think about them as one latent variable, all concatenated together. And you just write down the variational lower bound for that. So this is what the variational lower bound is. So that's the marginal likelihood. You have this average over all the latent variables, Z1 through ZL, together sampled from some kind of approximate posterior of this joint likelihood, this joint log likelihood of all the variables, including the observed data and the latent variables, divided by this thing. So that's how that works. And so some key properties you want for training models with multiple latent variables of this form are that this formula is fast to evaluate, and that it's easy to take a derivative of this. Otherwise, that'd be just too difficult to work with. So we can ask the question, is this thing actually fast to evaluate? So let's look at this thing at the top in the numerator. Is this fast to evaluate? No. Well, hopefully it is, because then this is not trainable. So it turns out that if you define it this way, then it should be fast. Because this model is an autoregressive model. Right? If all the variables are observed, all the z's and all the x's, then this is an autoregressive model. Sorry? Exactly. So it should be easy to evaluate the log likelihood of this. Yeah, sampling will be slow. In this case, though, you generally don't have as many latent variable blocks as there are pixels in an image. The deepest models go something like 20 latent variables, or 20 blocks of latent variables. So that's not too bad.
So would each latent variable be like a vector itself, or would it just be like one dimension of this overall latent?
Yeah, so actually this mathematical formalism works with everything. But in practice, what people call hierarchical latent variable models are the models where each latent variable is a block of components. So each one of these z's is going to be like a 4 by 4 by 128 tensor or something like that. It's like a block of latent variables. So what I just said with fast evaluation, or fast evaluation of this for autoregressive models, that's actually not entirely telling the true, that's not entirely the right thing to say. That generally is, that's only true if evaluating each conditional in an autoregressive model is parallelizable. But in fact, many of the hierarchical latent variable models that people define in practice are more like recurrent networks over the different z's. So that's actually not parallelizable. But maybe if you guys want to do some future work, you could make it parallelizable. Yes?
Wait, can you quickly explain that last sentence? Because people use all.
Yeah, so in practice, what people do to define these, like this, is they set each one of these to be a separate neural net. So that means in order to evaluate this likelihood, yeah, you could, but nobody's done it. So that's, with all of these, people generally design a network structure where you have to go in sequence. But you know, there's room for improvement. Okay, so that's how you train these things. Something else that you need is, well, as with any kind of VAE, hierarchical or not, it must be fast to sample from Q, because that's necessary for training. And so here, Q must operate over, must give you a sample from this hierarchy of latent variables. And so there are many choices for this. Generally, people design Q to kind of reflect the same structure as P. So there are a lot of very nice design for this. One is to have each Z be sampled as an IEF, and then chain those together in an autoregressive fashion. Another one uses autoregressive flows over these blocks. And yeah, I mean, if you're interested in more in how these models are designed, I encourage you to read these papers. They're pretty nice. And these models are state-of-the-art VAEs. So this model here, which was very recently released, achieves state-of-the-art results on many benchmarks among non-autoregressive models. So it's still the case that autoregressive models get better density estimation performance, but this is among the best in non-autoregressive models. Yeah.
Can you explain the comment on the previous slide that said autoregressive structures over layers? Does that mean with blocks?
Yeah.
Okay.
That's right. So that means sample one block, condition on that, sample the next block, et cetera. Cool.
Question?
Yeah.
It's a comment saying that VAEs produce blurry samples. Can you explain why that is, and why is it that these samples are not blurry at all?
Yeah, so I think the reason they produce blurry samples is because when people started saying that, people didn't train VAEs properly. So I think one of the reasons people say that is because there's like a squared loss in the VAE if you use a decoder that involves a squared loss. And so it's very common to say that squared losses like to blur things out. And that's why VAEs get blurry samples. But I think with these modern VAEs that have a lot more modifications to them, that's not necessarily the case anymore. So first of all, the decoder distribution doesn't have to be Gaussian. It could be like a weak autoregressive model. So there's no squared anywhere. Another reason is that both the prior and posterior can now be very powerful. So perhaps one reason why VAEs might get blurry samples is if the prior is not powerful enough, then it's sort of forced to sample something that lands like in the middle of two real data points. But if you have a very powerful prior, like an autoregressive one or one of these deep ones, then that's not true anymore. Kind of the same thing happens with the posterior. So if the posterior is very powerful, then it can sort of map data to fill all of space. Fill all the space under the prior so that there are no holes that correspond to blurry data. So I think that's how things used to be, but it's rapidly changing now. All right. Cool. So that wraps it up on VAEs. Now I'm going to switch a slide deck and I know this is a very abrupt transition, but live with me here. Okay, so VAEs are these nice likelihood-based generative models, but you can turn them into real compression algorithms using Bitback coding. So that's what we talked about the last time. So what that means specifically is that we want, there's a VAE elbow, which is something like average over data, average over Z drawn from Q, and then something like KL between Q and the prior. Plus this decoding term. Something like that. So that's a VAE objective. And it turns out that there's a way to turn a VAE into a compression scheme that achieves exactly this code length. So that's pretty cool. And how does that work? That's called Bitback Coding. And so these authors here noticed very recently that Bitback Coding is very compatible with this certain compression algorithm called Asymmetric Numeral Systems, or ANS. And this is, I would say, this is like currently the way of turning, like the best way of turning VAEs into real compression algorithms. So how does that work? The way it works is here, both the sender and receiver have the approximate posterior and the decoder, and also knowledge of the prior and so on. And so in order to send some data point X, as with all Bitback arguments, or Bitback coding schemes, we assume that there's some auxiliary information that the sender wishes to send. So that's going to be these initial bits over here. And then the sender is going to decode Z using the approximate posterior from the bit stream. So if the bits in the bit stream are uniform random, then decoding or decompressing from a random bit stream is the same thing as sampling. I'll show you why later. That might sound a little mysterious, but I'll show you exactly why that happens in ANS. So in other words, this samples. And then in the second step, the sender will encode X, condition on Z, using the decoder. And then we'll encode Z using the prior. So the first thing to note is that this is completely decodable. If it were not decodable, then this would be a useless scheme. But it is decodable, and the reason it's decodable is that all you have to do is go in reverse and swap encode with decode. So if you go in reverse, the receiver will decode Z, which is the latent variable, and then we'll decode X, given Z. So that's okay, because you can decode X from the decoder if you already know Z, and that is the case. And then the receiver will now encode Z using the posterior. This should say Q. And this is where Bitback happens. So you could say that this encoding is Bitback. That recovers these initial bits. So this is a concrete instantiation of Bitback coding. All right, so to make this real, though, we need some kind of compression algorithm that is able to do all these steps. We need this decode-encode algorithm that is able to achieve the right code lengths and is also able to work in this stack faction. So that turns out that right algorithm is called Asymmetric Numeral Systems. It's an alternative to arithmetic coding, which we learned about earlier. But I'm going to describe to you what ANS is now. So that's the guy. All right. What is ANS? I'll do it on this slide in honor of the guy who invented it. So let's say our goal here is to encode some sequence of symbols, A, B, B, A, B, so on. And let's say we know that each symbol A and B is drawn, is a coin flip. So it's drawn from a uniform distribution over those two. So what is the right thing to do here? Well, the right thing to do is to just, write it down. That you can't really do anything better than that. And the best code length you could hope for is just the length of the sequence. So let's say we assign A to 0. Let's start it with B, and B to 1. And so now I'll describe a very simple coding scheme that achieves the best code length. So the way that this is going to work is I'm just going to write down a binary number. And every time I encode a symbol, I'm just going to append it to the right. So here I have B, so that's a 1. And then I see A, so that's a 0. Then I see B, that's a 1, 1, 0, 0, 1. You got the point, right? All I did was every time I see a symbol, I just append a 0 or 1 to the right. So this achieves the right code length. But you know, if the data is not drawn from this uniform probability distribution, then the code length should be different. So ANS is a way of constructing such a scheme. So to describe ANS, for general distributions, I'll first describe how it works for this distribution over these two things. So what ANS does is it encodes a sequence of data points into a natural number. That natural number in its binary representation should have a length which is equal to the optimal one. So it's going to be n times the entropy of the data, where n is the number of symbols. So the way it works for this distribution is like this. We start with the natural number x, let's say 0. And whenever we encode A, what we do is we take x and we turn it into 2x. And in order to encode B, we take x and we turn it into 2x plus 1. So this x is the state of the algorithm that gets updated every time a new symbol is seen. And so if we start with x equals 0 and then we see the symbol B, what does this do to the binary representation of a number?
Appends a 1.
Exactly. So this appends a 1 on the right. If we see an A, well, that appends a 0 on the right in the binary representation. OK, so this scheme that I described here of appending 1s and 0s on the right, this is already ANS. This is the simplest form of ANS for a uniform distribution. But we want to come up with an analogous scheme for non-uniform distributions. And it's going to be of this form. So first of all, before I go on, let's make a remark, which is that if you just look at these rules here, this x updating rule, is it possible for you to decode the data? In other words, if I give you some x prime out in the wild, is it possible for you to tell me what was the last symbol that was encoded? Yeah, how do you do it? Exactly. So the way you do it is you check if it's even. If it's even, then it's A. That was the last symbol. And if it's odd, then it must have been B. And not only can you check what was the last symbol that was encoded, you can also get the previous state of the algorithm before that symbol was encoded. Right? So if x prime is even, then that means x, the previous state of the algorithm, must have been x prime over 2. Yeah, exactly. If x prime is odd, that means the previous state of the algorithm must have been, well, x prime minus 1 over 2. Right? And that's the previous state of the algorithm, and then you can keep on going. This is just a very fancy way of saying, just look at the binary digits, or the bits. OK, so how does this work in the general case? So let's say our two symbols are A and B, but now A occurs with probability 1/4, and B occurs with probability 3/4. How do we come up with an analogous scheme that gets the right code length? Well, this is how we do it. For every symbol, here we have two symbols A and B, we're going to define sets of natural numbers. And those sets, we want to be a partition of the natural numbers. So here's how we do it. So these numbers 0, 4, 8, we assign them to A. And the remaining numbers 1, 2, 3, 5, 6, 7, 9, 10, 11, we assign to B. So explicitly, we say that A corresponds to this set 0, 4, 8, 16, and so on. And B corresponds to this set 1, 2, 3, 5, 6, 7, so on. So I haven't told you how to do this, or why this is necessary, but this is just what we do. And we want these two sets to partition the natural numbers. So their union is the natural numbers, and they don't overlap. They have zero intersection. All right. And here's the encoding process. So suppose X is the current state of the algorithm, and we wish to encode A. So what we do, yes?
Do you update 12? For 8?
Yes. Yeah. Yeah, thanks. That's a 12. OK. So let's say we start with some state X. This is the current state of the algorithm. And we want to encode some symbol. So what we do, if we want to encode a symbol A, what we do is we take the number X, and we look up the Xth occurrence in A's set. OK, so if X is 0, let's say we start with X being 0 at the beginning of the algorithm, and we want to encode A. What we do is we look at A's set over here, and we look at the 0th element. That's just 0. So that means if we take A, if we start with the initial state 0 and we encode A, we get a new state 0. If we started with the initial state 1 and we encode A, then we get 4, because 4 is the element number 1 in A's set. Okay. Similarly, if we had the state 1, what if we wanted to encode B? What happens? Well, we look at element number 1 in B's set. So element number 1 in B's set is 2, right? So that's what this line says. So as you receive data, what you do is you take the set corresponding to the symbol that you wish to encode, and you take X, and you look for the Xth occurrence inside that set. OK, so if this scheme were any useful, then it should be decodable. Meaning, given any state X prime in the middle of the algorithm, we should be able to tell what was the last symbol that was encoded. Can we do that? Yeah. Yeah, so here, mod 4. But generally, why can we do that?
It's invertible.
Right, so we can do this because we define these sets here to partition the natural numbers. So that means that every number can be uniquely identified with a symbol, A or B. In other words, if X prime were 9, then we know that lands in B's set. So that means the last symbol encoded must have been B. Yeah? And not only that, we can also recover the last X, the previous state of the algorithm. And the way we do that is, well, here, if we got 9, then it must have been a B. That was the last symbol. And then we can ask, what is our index into B's set? So the index into B's set is 0, 1, 2, 3, 4, 5, 6. So 9 is the 6th number in B's set. So that means the previous state must have been 6. See, all this works. All of this works is, the reason is because we define these sets to be a partition of the natural numbers. So ANS, what is ANS now? ANS is this scheme, or I should say RANS, which is defined in the ANS paper, is this scheme with exactly this kind of partition. This kind of partition that looks like this. So the stuff that I was just talking about isn't very particular to the type of partition you choose. It's just very convenient to choose this one because it repeats very often throughout the natural numbers. And it turns out that there are some very nice, elegant formulas that can do these encoding and decoding operations in a single line of code, which is really cool. All right, and so the final, yeah.
So does this mean that, like, for example, in this case, the probabilities were 1 over 4 and 3 over 4.
Yeah.
If they were 223 over 225,
Yeah,
2 over 225, then it would be.
Yeah, so what you have to do in this scheme is convert all the probabilities into rational numbers. So that you have to approximate. But assuming you're willing to do that, then you can define these sets in a very similar way. So if it were like 5 out of 100, then 9 out of 100, and so on, then you would take the first 100 natural numbers, call the first 5 corresponding to the first symbol, the next 9 corresponding to the second, and so on, up until 100, and then you keep repeating. So that's the construction. OK, so I hope we're all convinced that you can encode stuff and you can also decode stuff without losing anything. So that's fine. But does this achieve the right rate, the right code length? The answer is, well, what does it mean to encode? Well, if you encode, that's basically like dividing by the probability of that symbol, right? So here, every time we encode a number A or a symbol A, we multiply the number by 4, right? That's like dividing by 1/4. And similarly, every time we encoded B, that's like dividing by 3/4, effectively, kind of on average. So what that means is that if we encode a whole string of symbols, S1 through ST, this is the final number we get, right? Approximately. It's basically like taking the first symbol and dividing it by all the probabilities, which means that the number of bits in the binary representation is the sum of the negative log probabilities, which is optimal. Right? So that means if we wanted to, say, encode some image X in, I don't know, say using in the decoder part of a VAE, and we do this to convert it into a binary string, that binary string will have length negative log probability of X given Z. That's exactly what we want. OK. Are we good? OK. One final point, which is I think a lot of people asked last time, why is decoding random bits like sampling? Right? That was like that's the first thing we have to do here, right? Decode Z. Why is that like sampling? Assuming the initial bits are random. Well, if we assume the initial bits are random, so again, these are A, and the rest are B. If the initial bits are random, that's like choosing a random point on the natural numbers, right? And if you decode from a random point here, because the symbols correspond to the sets that are distributed with the densities corresponding to the probabilities, that's like sampling. Right? So if I choose a uniform random number from 0 to 3, that's the same thing as sampling from A or B according to these probabilities. Right? Because 0 is probability. In this set of 4 numbers, 0 has the probability of 1/4. And the numbers 1 to 3 have probability 3/4. So this is why decompressing noise is the same thing as sampling. OK, I hope that made sense. OK, that concludes this part of the lecture. Let's switch.
All right. Can we get started? Cool. So, how many of you are bored of density models?
Never.
Never?
Never.
Okay. Nobody? Cool. So, we're going to get into another class of generative models, which will be pretty new. And also, it's a sort of an emerging research field, so like a lot of theory is yet to be done in this. So it's going to be more like an engineering discipline kind of a lecture. So we'll talk about implicit models. So far, you've seen autoregressive models, made pixel RNN CNN, gated pixel CNN, pixel snail, subscale pixel nets. You've seen flow models, nice autoregressive flows, real MVP, glow, flow++. And then you've seen latent variable models, wake sleep, VAE, importance weighting, VAE, autoencoders, IAF, VAE. So all these models, what's the common point between them? They're all maximizing likelihood, either approximate likelihood or the true exact likelihood. So for instance, flow models and autoregressive models are trying to exactly optimize the likelihood, whereas VAE or IAF VAE, they're trying to optimize a lower bound on the true log likelihood. Now, what if your objective for working on generative models is just to build good samplers, right? All these models you've seen, density models, are generative models, but they're, apart from being generative models, they're useful for compression. And you've seen a lot of compression as well in the first part of the course. But if you only cared about the generative part, all you want is you want to sample from a model, and you want the distribution of samples that you get from your sampler to be approximately the same as the distribution of true data points. That's all you care about. So here's a question. Do you need to optimize log likelihood for that? Like a first principles question, rather.
No.
I mean, I guess you probably say no, because that's the whole point of this lecture. So how about this sampler?
No.
Yeah. So can we call it done?
I don't like it.
So this is just copying the files randomly. So obviously you don't want this, right? This is, but you can get you can't get better samples than this particular model, like no matter what you try. Like this is just going to be as photorealistic as it can get. Only inaccuracies being the digitization in your camera. So you don't just want to sample the exact data points. You want to build a generative model that can understand the underlying distribution of data points. You want to smoothly interpolate across the training samples, output the samples that are similar but not exactly the same. So for instance, if you have MNIST data set, you want to output digits whose strokes are not seen in the training set. That's the only way someone knows like the generative model has truly understood what's underlying distribution. And if you have celebrity faces data set, you want to output unseen poses, different lighting conditions, different skin textures, so on. So let's look at the graphical model again. You have unobserved true latent variables, and that's being passed through some deep neural net or some any function, and you get the data samples which you're observing. And so does this sound familiar? Like, is this what you've been seeing all along, the same thing? Sample Z, pass it through a neural net, get X. Like we saw this in flow models, like you had this. You had this in VAE as well. So what's going to be different here? So we're not going to optimize likelihood of x. That's the difference. You're just going to sample from this neural net. It doesn't matter if it's a likelihood model or not. And if that's the case, how do we design an objective function for learning this neural net? So that some neural net takes in the noise and outputs something of the size height cross width cross number of channels. And I'm telling you that there's no likelihood here. So, but I still want to make sure that this particular tensor looks like an actual image. So how do we design an objective? Any ideas?
Make a deeper network that learns some metric to tell you whether this is like close to being a
Yeah.
likelihood or not.
Yeah, exactly. So you're outputting some samples, but you have some true set of samples, and you want some kind of critique or some kind of reward or whatever that tells you how good you are at the moment, and that should be sample based. That is, you only have samples. You don't have the true distribution of either your data or the model. So how do you just compare a bunch of samples and refine the neural net continuously? That's the idea. So p data, x1 to xn, you have a sampler, which is a deep neural net, some function of parameters phi, and x, you get it from the sampler as q phi of z. Now this induces some kind of density called p model, but we don't have an explicit form for p model. Whereas in autoregressive models, you could write p model as like some log p xi given the parents of xi, but here you can't write that because you're not actually optimizing or outputting any kind of log likelihood here. So without an explicit form for p model or p data, just using the samples, try to get p model as close to p data. So try to learn an appropriate phi. So that's the whole idea of implicit generative models. So far, so good. Any questions? Okay. So why is this a departure from maximum likelihood? In maximum likelihood, what were you doing? You optimize KL of p data and p model in this direction. Because if you write that down, you're just going to get expectation log p data by p model over p data, and the other term is just the entropy of the data distribution. That's not dependent on your model. So you just optimize expectation over data points log p theta x. So that was what you were doing so far. And instead, if we don't have an explicit p theta of x, we probably can come up with other kind of distance measures like maximum mean discrepancy, Jensen-Shannon divergence, Earth-Morris distance. These behave differently from KL divergence. We'll see how. So one obvious idea to start off with, something you probably are familiar with from statistics. When you just have two different distributions, but only the samples, what can you test to say if they come from the same distribution? The naive thing that you would do is just calculate the mean and standard deviation and check if they're the same, right? Assuming that they both are Gaussians. You just want to see if they have the same moments, the first two moments are the same. So that's the naive thing you would do. This would probably work in low dimensions, but it's not feasible to compute higher order moments. Higher dimensions, more complex distributions require you to get larger, you want to compute higher order moments, and those are going to explode as the number of dimensions increase. So this is not feasible. So what people in machine learning do when something's not feasible, they invoke the kernel trick. So okay, so let's look at the maximum. So this is the maximum mean discrepancy loss. So xi, a set of points coming from one distribution, yj, a set of points coming from another distribution, and this particular term, 1 over average phi xi minus average phi yj, is the maximum mean discrepancy term. And now you can choose your phi here. But let's estimate this for a generic phi. Now you can expand this out, and you can get these three different terms. So these look really familiar to you, right? A bunch of dot products. So that's why you can invoke the kernel trick, where you can say that this is like some kernel function of xi and xi prime. This is xi and yj. Sorry, this one is xi and yj, and this one is yj and yj prime. So this is a mathematical intuition here. So if you use the identity function, it's just the same as sample means. So just 1 over n average xi, 1 over m average yj. You're just trying to learn. You're just trying to minimize the difference between the means of the two distributions. That's not going to do much. That's just going to get you the mean mode. But the kernel trick allows you to get into higher dimensional spaces. You can use some universal kernel like the radial basis function kernel. And so this person actually has 2 papers on this topic, where he actually says that you can prove that when you use this particular kernel and under certain conditions, this particular maximum mean discrepancy loss accounts for all the moments in high dimensions, not just the first moments or second moments. So there is a principal reason for people working on this. It's not a random kernel trick. The architecture is called generative moment matching networks. A caveat that this idea came after GANs, but I'm covering it before because I want to enforce the novelty in the GAN architecture using this as a reference point. This is a very nice idea as well, but this is what like a machine learning or statistics person would come up with when they're trying to match 2 distributions without access to the actual density functions. So the generative moment matching network, you sample a z and you pass it through a deep neural net and you get sample x. It's sigmoid because they work on MNIST data sets here. Don't worry about the second part for now. So this is how the algorithm works. You have a bunch of data points. You have a prior, which could be a uniform or Gaussian, and this network, which is just a feed forward net. And you sample a mini batch of data points, and you get a new set of samples from your model, and you compute the maximum mean discrepancy on these 2 batches. You take a gradient step to update your weights. So that's just how the moment matching networks works. It actually produces reasonable samples. So you can look at the MNIST samples or the phases TFT data set. Works reasonably fine. And it also seems, so just like I said, for universal kernels, it corresponds to minimizing the difference between several higher order moments. But the problem with this idea is that it doesn't scale well beyond MNIST and the TFT phases. The reason is that for the kernel trick, you can see several pairs of points, the cross term here. You need, as your data set keeps getting bigger, you need larger and larger batch sizes for computing this loss and computing the gradients. So even for this paper, which was done in 2014 or 15, they use a batch size of 1,000 for getting all this to work, which is pretty big. So that's why this idea never really got adopted for large scale. And also, it turns out that you need multiple kernels, not just a single band. It's not just a single sigma. So you need several sigma I, and you need to take a mixture of these kernels. So and also, they need to use some autoencoder representation for learning the moment matching. So they don't directly output the pixels, but they output they learn a denoising autoencoder, quantize it, or rather binarize it, and then learn a moment matching network to output the latent space of the autoencoder. So that seems to work better than the direct pixel space moment matching. So all kinds of tricks needed to make it work. Let's see. Maybe we should take a break here because I need to cover GANs after this. Cool. Oh yeah, you can. Yeah, go for it.
Question about the different kind of metrics that
Yeah.
we use. I recently heard about something called analysis buckets, where essentially what you do is that you sample some, whatever embeddings you want to sample, sample some vectors and elements with, and then you do this matching process where you assign.
Okay. So are you guys like suggesting the projects and all?
Oh yeah.
Sometimes
So we are working on it. We made a list of like 10 ideas so far. I think once the other like yeah, more ideas are pulled in.
And those include things that are not taught till, right?
Um, I guess it's probably mostly like after this lecture. I think the generative model.
I think
part of
GANs
it-
is the most
Yeah.
biggest part of this.
Yeah, so GANs will be more or less done today.
Hmm.
And after that, I think it's like.
Just lectures.
No,
Sorry, I
we
mean-
have representation learning
Hmm.
and some how to use generative models for RL, those kind of things. But after that, it's going to be guest lectures. So more or less, like say, 70 to 80% is done. So you'll probably be able to understand most of the
70 to 80% is done.
as in the yeah. So
The core knowledge.
yeah, so 2 more weeks for like main lectures,
Okay.
and then it's going to be like one part of the class might be a main lecture, but one part of the class is going to be a guest lecture. So that's why I said like 70 to 80% will be done. So I think ideas, project ideas, you'll be able to understand more or less all the different ideas.
Okay.
Yeah.
And now when you told that this implicit models,
Yeah.
like how different is it from GANs?
So GAN is one kind of an implicit model, which is what I'm going to
okay.
cover now.
Okay,
But
implicit model is the big thing and GAN is like
yeah,
implicit
so
is like
GAN is one way to learn implicit models, but like say moment matching is another idea, and one way to implement moment matching is to use maximum mean discrepancy, and so that's also an implicit model. So implicit model is basically any kind of a problem where you don't have an explicit density function for the data or the model, and but you still want to get them close as much as possible. So that's what
so when you say implicit models, like lots of research is going on these days. So it includes all of these things like GANs and everything.
yeah.
Right.
Yeah, so GAN is
And
the
then
most
after that,
successful version of it.
Implicit model.
Yeah, so if you were to work on implicit models, it's hard to have a reason not to use a GAN and use something else, because the success and the level of engineering that has gone into like making implicit models work is really a lot.
I mean, because after that you said that these things have not been done a lot because these things need a lot of
Yeah.
like
Moment
Six Sigmas
matching.
and
Yeah.
lot of
Yeah, so that's moment matching.
So moment matching is not so practical, but as an implicit model which includes many different things, like have a lot of scope in research.
Yeah, so there are like other versions, like you can, there, yeah, so there are other kind of implicit models which just try to map a bunch of noise vectors to data points, and then try to keep changing the noise vectors in addition to the mapping. So that has nothing to do with GAN, but it also produces good samples. We might cover it next week.
And for the last project, so
Yeah.
I'm trying to submit it to the same days. So getting many nans basically. So what I understood is like to get rid of nans, we do data dependent installations and preprocessing and all those things. So
Okay.
I did, and I'm still getting nans. So I think maybe the act norm implementation is wrong. So what I wanted to clarify. So we have, let's say, like batch of let's say 10 images, and each image has like 3 channels. So when you say act norm, you do like centering and dividing by the standard deviation channel wise. That is channel wise per image, right?
No, across images, across your batch.
Across the whole batch, across all the
So
height and
you're
width.
taking the axis mean. I mean, when you take the mean, you take the average across the first 3 axes. So that I mean, if it's in HWC format, yeah.
So like I give it 10 images, and it will give me 3 numbers. That's it, right?
Yep. Yep.
And those three numbers will be.
It depends on which channel you're implementing, like which low model, which layer you're implementing it. If the number of channels is more, it can give you as many numbers.
Oh, I mean, yeah, I understand. I mean, depending on the channels. So whatever the number of channels will give the same number of outputs, and that needs to be subtracted and divided.
Right. Yeah.
That's what I was doing for image.
Okay. Yeah.
So these slip tests are only for homework or also for project? Like, will there be
What do you call it? What do you do?
slip tests 7 days that we get?
Oh yeah,
Only for the
it's only for the homework. I think.
project will be separate.
Yeah, project is like a presentation at the
Yeah,
end.
but for the reports or something like in between intermediate days,
Oh, the milestone you mean?
if we need extension on that, it's not like.
Yeah, I'm not aware of the policy on that. I don't think it has a late days policy. Okay. So let's resume. Cool. So we saw how the moment matching networks has a problem with scaling because of multiple reasons. One being the batch size dependence, another being the requirement for using several bandwidth kernels, and also requiring some kind of autoencoder. Let's see the actual idea that we want to talk about. Generative adversarial networks. Like I pointed out already, this paper came before moment matching. So it was done by Ian, Goodfellow, and others. And the key idea here is you formulate the implicit model problem as a two-player minimax game between a generator G and a discriminator D. The discriminator tries to perform a binary classification task where it's trying to say whatever is the actual data point in your true data distribution is 1, and what the generator spits out is 0, or basically the real and fake classification. And the generator tries to use this discriminator to improve itself. So it performs updates on itself so as to fool the discriminator into thinking that the samples it generated were real instead of fake. And that's what is formulated in this loss function. This is expectation over the true data, and this is expectation over generated data points. And these two terms are just your log likelihoods, or the binary cross entropy loss. So simpler visual explanation is this. You're sampling noise, feeding it through a deep neural network. It's a differentiable function G, and you get X. You also have data points from the real data distribution. Both of this is the same function D, and D tries to make D of G of Z near 0, and G tries to make D of G of Z near 1. And also D is also trying to make D of X close to 1 for true X. And hopefully, the hope is that this game converges and to a point where the discriminator is kind of like a random classifier. It's not able to say about the generated data and the true data points. So that's often referred to as the saddle point or the fixed point of this game. So here's a question for you. What is the optimal discriminator given the generated and the true distributions? So just to write it down. So the cost function is this. Expect the binary cross entropy over the true data points and the generated data points. And you can write down the integrals of the expectations, and you can assume that let's assume that this support is shared across the generated data points and the true data points, so you can club them into one integral. So this is the cost function. Now, a simple question is, if I try to find in the function space, like among all possible d of x, what would be the optimum for the discriminator to optimize this particular cost function? What's that going to be? Any? Oh, yeah. I'm still new to this iPad thing. Can you try to just find the derivative, set it to 0, and figure out the optimal discriminator? Yeah, so that's what you need to do to find optimal discriminator. You can set, so it's some function of y. If in the function space, it's some function of y, a log y plus b log 1 minus y. So the y star is a by a plus b, as long as a and b are not zeros. So this is the optimal discriminator here. P data x by P data x plus PGX. PGX is the induced distribution. Note that we don't really know what PG is or P data is. This is just a mathematical form. We don't really have any functional or exact values to evaluate these two quantities. But we'll use this to understand something else. So that's the point of doing this math. So what does this actually mean? So if this is the true data distribution, and this is the one that the model generates, the green, the discriminator is just going to be like this. So wherever the P data is high, it's going to be close to 1 there, because it's P data by P data plus PG. So, and it's going to be close to 0 when the data distribution, the P data is going to go down. So here, as it keeps going down, the discriminator goes down as well and goes to 0 over here. And in the middle, it's in some kind of proportion. So where it keeps reducing as the data distribution's PDF goes down and the model's somewhat coming down slower. So yeah, so this is a figure taken from the original GAN paper. Now the next question is, what is the generator objective given the optimal discriminator? So if you write down the V, so you have the cost function, this particular term. If we can substitute d star of x here, we would get the cost function that the generator optimizes given the optimal discriminator. So it's almost like we find out this part of the problem completely and then try to solve the outer problem. We just want to understand the functional form for that problem. So if you again substitute it, this is very simple math. You just write down the expressions and add and subtract log 4. You get this particular, this pair of KL divergences. And this is referred to as the Jensen-Shannon divergence of P data and PG. It's a symmetric divergence measure. And it has a fixed point when PG equal to P data, with the value being, with the value of the cost function being minus log 4, this would go to 0. So the understanding is that for the optimal discriminator, the objective function that the generator is trying to optimize is to minimize the Jensen-Shannon divergence with a true data distribution. And that's why this is referred to as a departure from maximum likelihood training, because it is not minimizing the KL of, so maximum likelihood you were trying to do KL of P data and PG. Here you're doing, instead you're trying to optimize the Jensen-Shannon divergence. Note that this is just math. Like, it's not actually the case that in reality, when you run GAN, this is the metric being optimized, because this metric is intractable. You don't know P data or PG. So this is just to understand what this could be a potential explanation as to why GANs behave differently from maximum likelihood. Okay, so this is a very neat paper. I really recommend you guys go and check it out. A note on evaluation of generative models. So they did a nice experiment here where they took a mixture of Gaussian's true data distribution here on the first figure, and they tried to fit a isotropic Gaussian to this distribution. And if you try to optimize the KL divergence between data and the distribution, you end up with somewhere in the middle. So this is how maximum likelihood would behave when you don't really have an expressive model. It'll blur the modes that are present in your true data distribution. The maximum mean discrepancy, which we saw earlier, would try to fit one of these modes, the dominant mode, and Jensen-Shannon divergence is even more aggressive than that. So that's why I said it's a departure from likelihood-based training. There is a clear difference between what's happening. We can actually try to understand this using a very simple example. This is a figure taken from the deep learning textbook, chapter 3. Yeah.
Why does the fact that KL divergence isn't a good metric for fitting that Gaussian just directly imply that a maximum likelihood-based model won't work?
Because maximum likelihood is KL of P data and P model.
Sure, but
yeah.
like, is there another way to like, could we make a maximum likelihood-based approach that instead of using KL uses like the Jensen-Shannon divergence?
Yeah, you could, but that's not what maximum likelihood objective. Like, you can design a density model to do something else, but in general, by maximum likelihood, I'm just calling a log p theta x average over data points. Yeah. Let's try to understand why this is the case. Why this particular objective prefers blurring modes while the other prefers fitting one mode. So it's often in people refer to as mode seeking for the JSD case, and so why does it happen? So you can write down this KL. Let's say PR is the true data and PG is the generated data distribution. So how would this look? So integral PR log PR by PG. All right. So now if PG equal to 0 where P real not equal to 0, if this is the case, this term would go to infinity, right? So you get a minus log 0, and that would go to infinity. So your generator or your model distribution should not have a 0 probability mass where the real data distribution has a non-zero probability mass. So it's very important for the KL divergence objective. So that's why no matter you're okay placing probability mass on points where the data manifold isn't really present, as long as you can place probability mass everywhere the data manifold is. So that's what you care about more. You don't care if you are producing some unlikely samples. You just want to make sure that all the likely samples are covered under your density model. Now if you write down the battery is going down. So if you write down the opposite, KL of PG to PR instead. So that's going to be of the form PG log PG by PR. So now if PR equal to 0 when PG not equal to 0, that is, if your generated distribution assigns probability mass to any place where the data manifold has 0 probability mass, you're aggressively penalized. So this better make sure that even if you don't cover some of the data manifold points, as long as you're completely only assigning probability mass to whatever is in the data and nowhere else, you're good. So that's why the JSD, MMD, they behave in a different way. KL divergence behaves in a different way because this notion of the reverse KL comes in there, and that tries to fit only one mode aggressively compared to averaging over modes. So often, yeah.
Where's the reverse KL term in the MMD objective?
Oh, right. So not explicitly. So this is just what is empirically observed. So there is no explicit reverse KL term in the MMD objective. Yeah. Yeah. So this is also why people often say, like, another reason for blurry samples is your averaging all the values in your data set because you don't have an expressive model. And so that's what a likelihood model will do. That's also one reason to understand why GANs produce really good samples, not necessarily because they cover all the data set. They just make sure that they only output very likely samples. But yeah.
Do you observe that in practice, that GANs don't cover the entire data set?
Yeah. Yeah.
How does that manifest itself, like in interpolation?
Interpolation, there are other ways to measure diversity. Like people have come up with inception scores, kind of evaluation metrics. Also, you can just look at all the samples the model outputs. You'll just be getting pretty much the same thing. All right, so here's a trade-off. For compression, one would prefer to ensure all the data points in your distribution are assigned probability mass, which is why it makes more sense to work on likelihood models if you care about compression. But if you're someone who just wants to generate good samples, the blurring across modes spoils the perceptual quality because of this assigning non-zero probability mass to points outside the data manifold. So better looking samples are possible if you just pick one mode and focus on it, but that's not. So the point of this slide is to tell you that at the end of the day, it's about what you care. If you're working on compression, you don't want to work with things that just pick out one mode. So again, the caveat is that you can progress more on density models as well, make the models a lot more expressive. Hopefully, that will ensure that these kinds of blurry modes are avoided. All right, back to GANs. So we had this cost function, min-max objective, and we saw this is the inner term is the discriminator. So two questions for you. Is it feasible to run this to completion, the inner loop? You saw the optimal has some particular functional form. Like, is it feasible to run it to completion? And the second question is, for this specific objective, like for this specific kind of functional forms for the loss function, if in case you ran it to completion, would it create problems? Any thoughts? Yeah.
It's like very non-mathematical, but maybe we get a kind of, like if our goal is to end up with a good generator,
Mm-hmm.
then we might just end up with a discriminator that's too good,
Mm-hmm.
so our generator doesn't end up learning anything.
Right. So the point was that the discriminator could be too good for the generator to learn anything. So intuitively, that's what's the intuition is right. That's what's going to happen here. So this is very simple. Let's say the discriminator perfectly succeeded in its classification task, where you had a bunch of generated points, you had a bunch of true data points, and it learned a perfect binary classifier. So the generator is going to use this particular term. It's going to try to improve this by backpropagating to the input it fed into the discriminator. And the output of the discriminator is some sigmoid function. And we know that the derivative of a sigmoid is product of sigmoid and 1 minus sigmoid. So this red curve is sigmoid, and the blue curve is the derivative. So wherever the sigmoid is 0, wherever the discriminator outputs 0, which is samples from the generator, the derivative is 0 or close to 0. So the generator cannot really improve from this if the discriminator is already pretty perfect, because even though the discriminator works fine, the gradient it gets because of this particular functional form of the discriminator is 0. So people call this as the discriminator saturation problem in GANs. People often say, "Oh, the discriminator is saturated." So that's what happens if you use this min-max loss. So one fix for this is not to run the inner loop fully. You just alternate between the two gradient descent steps. So you treat this as two different loss functions. The first is the discriminator objective, which is just I have a negative sign because it's a loss function. So and so that's the discriminator is trying to minimize that, and the generator is trying to just have the opposite sign of this loss. And I'm just writing out the second term because the first term has no generative parameters in it. So if you just take gradient descent steps on the parameters of the discriminator and the generator respectively, this somewhat fixes it, but not really. In practice, it's still super hard, unstable. And so Ian Goodfellow suggests modifying the generator objective to make it non-zero sum. So one way to do that is, instead of trying to minimize this, which is probability of misclassification, you can try to maximize log d of g of z. So basically, the generator can just maximize the probability of it being correct instead of trying to minimize the probability of being incorrect. So that makes it a non-zero sum game from now, because the discriminator tries to minimize the probability of generator being maximize the probability of generator being incorrect, whereas the generator tries to maximize the probability of it being correct. So it no longer is a zero-sum game. And it's a very heuristic fix. There is no theoretical analysis on this game anymore. Yeah.
How is it not zero-sum? Because the probability of it being correct in being
Oh, yeah. So this is the loss, right? So the loss for the generator is now modified to expectation z log dgz, right? So the two objectives don't add up to 0, this one and this.
Got it.
Yeah.
Do you need to modify to the discriminator's loss function?
We don't need to, because the discriminator is just a binary classifier. You could do that. I don't know how you would do that, but yeah. So this is still a heuristic fix. It's not like it really solves the problem, but it was used in like TC GAN and other important architectures, so that's why I'm presenting it. So here is the pseudocode for GAN from the original paper. You sample a bunch of noise vectors. You sample data points. You update the discriminator. So here, note that there is a for loop over k steps. So the original paper suggests taking k gradient steps on the discriminator for every gradient step on the generator. But they use k equal to 1 in their paper, so I don't know why this was pointed out. But yeah, maybe for the non-zero sum game it was used. Maybe that's probably part of the code, but it wasn't in the paper. And the generator is just trying to optimize the negative of the discriminator's objective for the generated points. And you do this gradient descent using momentum. Yeah. So people often talk about this term mode collapse. I'm sure all of you have heard it, where people talk about GANs. So what is mode collapse? So let's say the target distribution is some 2D mixture of Gaussians like this in a circle. And if you just try to optimize a standard GAN here, so this is what happens. It oscillates across these modes, doesn't converge. This was an experiment done by a paper called Unroll GAN. So you can think about this as given a good discriminator, the generator is just going to try to fool it as best as it can. So it will try to assign all probability mass on one mode so that the discriminator cannot really distinguish if that came from the data or the generated distribution, because even if the discriminator doesn't cover all the modes, whatever it outputs seems like a real data sample. So it's hard for it to discriminate from what is true data and what is generated, even though the generated doesn't cover the entire data manifold. So that's referred to as a mode collapse problem. There is no one single explanation for why it happens. There are lots of reasons. So instability in training, the different kind of divergence that's being optimized here, all are different reasons for it. So yeah, so actually this slide should have been before, but yeah, this is what I was talking about when I said non-zero sum. So the objective for the generator changes here, and this somewhat helps address the mode collapse problem and was adopted in other architectures that followed GAN. So how did the first GAN paper evaluate what they did? It's hard to evaluate GANs. Like, it's still an open problem now. So they do something called parse-in window density estimation. So how does that work? How many of you are aware of it? Like fitting, okay, just one? Okay. Okay, so I think it's worth going over it because you've seen all density models so far. So it's a very simple idea where you try to, so let's say you have some weird distribution like this. One obvious thing to do is fit lots of histograms around its distribution and take the density from each. So if you had a unit cube around a point x such that any point inside the unit cube is assigned a value 1 and any point outside is assigned a value 0. So call that as some really primitive density model. So you can find out the density around a particular center x as k of call this function k that outputs 1s or 0s as described. So you can output you can have a size h centered cube with with this particular function. So this will capture the sum over all data points xi would capture the density at point x, the number of points that are falling into this particular cube. And if you pick a bunch of centers and windows and try to estimate the densities around different centers, add them up, evaluate this on the validation set. So that's what you would get as the parse-in window density estimate. This is a very approximate way of doing it, hard to do it in high dimensions. The original GAN paper was written in MNIST, so they were able to do it. So it works as well as the other energy-based models at that time. We've not covered energy-based models, so you don't have to worry about it. The intention of this is to show that the evaluation of GAN is hard, and they had to come up with approximate ways to show their model works reasonably well. And the samples. So you saw in the first lecture big GAN, style GAN samples. Would you believe that if I said this was only 4 years ago that the samples were this bad? Like, these are the actual CFAR samples. And phases, MNIST. MNIST is reasonably good. Phases okay, but CFAR is really bad. So to summarize, key pieces of GAN was that it allowed fast sampling, and it wasn't doing any kind of inference. So in the first paper, Goodfellow suggests that you can actually run approximate inference by, once you train a GAN to convergence, you can invert all the z to x. So you had z to x mapping, so you can invert that from x to z and build some kind of an inference model. Nobody has really done that. So notion of optimizing directly for what you care about. So this is somewhat like a heuristic statement to make, but what I'm trying to say is, but if you care only about generating perceptually high quality samples, that's what it's doing, because it's trying to fit only points that are highly probable and not points that are not probable. Cool. So let's see. Jonathan, I have only 2% charge on this. I have only 2% charge on the iPad. So So best to switch, right? Yeah, I'll use my laptop.
Quick question about this. Has anybody tried for the noise about the inference again?
So that's pretty interesting because it turns out that it's a very different train again or train to flow. Like go down or it doesn't train. So yeah.
Oh. Thanks. Okay, great. Thanks. Cool. Any questions about GAN so far? Cool. So the next GAN that we're going to talk about is deep convolutional GAN, or DC GAN. It's done by Alec Radford and others. Alec would be giving a guest lecture in this course. In some sense, this paper really was super important for getting a lot of people to work on GANs, especially people from computer vision fields, because the original GAN was still like a machine learning idea, whereas after this paper, the sample quality in GANs went up so high. So this is the architecture. So this was considered deep in 2014 or 15, so you should take it as deep. So you take a 100-dimensional noise vector, and the first layer is fully connected, and it's reshaped to a 3D tensor, and after that it's just a bunch of deconvolutions or transpose convolution, the way you call it, with strides. So, and finally it tries to get to the image, which is 64 cross 64 cross 3. So here are a bunch of design choices. Let's go over them one by one. The first thing they point out is architectures that worked well for supervised learning weren't good for GANs. So what they did is they got rid of spatial max pooling and went for an all convolutional network design using strided convolutions. And barring the first projection layer, that is this layer that we saw here, everything else is convolutional. And another thing they use is batch normalization. They say that it helps preventing mode collapse when training deep models. But crucially, they don't apply it everywhere. They don't apply it at the output layer of the generator and the input layer of the discriminator. So that was a very important design choice. And Ian Goodfellow's GAN used max out as the activation function. So they changed that to ReLU. But they also observed that for discriminator, they needed the leaky ReLU. So leaky ReLU is basically ReLU with a small slope for the negative part. The slope is like 0.2 or something. And then the discriminator outputs a sigmoid because it's doing a binary classification task. They use atom instead of momentum STD. They also make sure that the momentum is really small. And the inputs are, the generator outputs a tanh activation function because the inputs are scaled to -1 to 1. So for people who may think this is kind of boring, all these are super hard and non-trivial choices. It's almost like these people ran architecture search, just that they are super intelligent. So you can look at the samples. So compared to the GAN samples you saw just a few slides ago, these are way better. And also they were trained on millions of images, not small data sets like CFAR or MNIST. So they use millions of faces, bedrooms, and show like really good samples. These are the samples from faces. So they just Google search people, got their faces, and used some OpenCV bounding boxes to crop the faces, and created a data set on their own. And you can also see how this is interpolating really smoothly. So these are different bedrooms starting and end. And you can see how the smooth transitions are observed, even in high dimensions. And first time ImageNet samples from a generative model. So that was pretty big. All these samples are looking really good. In fact, likelihood models, only now they're getting to output these levels of samples. So another cool thing with DC GAN was that it was the first model that kind of brought in all these ideas from word2vec to computer to vision-based unsupervised learning. So what they did is they picked average of 3 smiling women faces, the average latents of these 3, added it to the average latents of neutral women, and they got a neutral added a neutral man's average, and they got a smiling man samples. So the latents are capturing notions of neutral, smiling, man, woman. So that's really cool. Though it wouldn't work if you use just a single image, they point out that unlike in word2vec where you can just take a single word and do all these things, here you need some kind of averaging over 3 different inputs to get all these working. Yeah.
Are the vectors for the smiling women close together in some sense compared to the neutral classes?
Yeah. Yeah. So there must be some noise vector that captures this, fires 1 or 0 for these things. So you can other kinds of interpolations. So with glasses, without glasses, and add a woman, get women with glasses, So, and they also show that this thing would fail in the pixel space. So if you just try to do this in the pixel space, you'll get all these blurry, weird faces. Other interpolations, you can go from different orientations of the face. So looking towards the right, looking towards the left. So they had to do a lot of engineering to get the data for all these things. So they also evaluated on representation learning, which was kind of not very common for generative model people to do. So they trained a DC GAN on ImageNet 32x32 and took the discriminator and pooled all the features at different levels and concatenated them and built a linear SVM on top. And they showed that the accuracy you can get is better than other algorithms that were sort of very popular at the time, like using k-means with some learned random features. Adam Coates wrote a paper saying if you just use random features and run some kind of k-means, you can get really good accuracies without any labels. So it was not as good as other self-supervised learning methods, but note that these 4 were trained directly on CFAR and tested on CFAR, whereas this one was not trained on CFAR, it was trained on ImageNet, and then the features were found out to be pretty useful for CFAR. So that's a pretty good success story for representation learning. So the key achievements from DC GAN was that you got really high sample quality for the first time. You got large images, could do some representation learning, very cool vector space arithmetic interpolations, scales well to real scenes, bedrooms, and probably most probably, like I'm not 100% sure, but this is the first generative model to produce ImageNet bedrooms, celebrity samples at scale. So everybody was pretty surprised by this. And but what is the issue even after this? It's not like GANs were solved after this. So if you notice, like all these are pretty non-trivial tricks, and different tricks work for different data sets. So in fact, in their repository, they have one folder for each data set. So so it was kind of brittle, and it's not very robust to architectures or hyperparameters. But it was still a big deal. And that motivated the next work called Improved Training of GANs, done by Tim Salimans and others. Pieter Chen is part of this paper. Here he is. So proposed like 7 different tricks, or 6 tricks and 1 evaluation metric. We are going to look at them one by one. Feature matching, historical averaging, minimatch discrimination, virtual batch norm, one-sided label smoothing, and some semi-supervised learning. And also proposes an evaluation for GANs, which was not done at that time, called inception score. That became really popular, and like every new GAN paper written now uses their code for running inception score metrics. So what is feature matching? So we saw that the generator trying to directly optimize the discriminator's output leads to all sorts of instabilities and problems. So what if you could just match the features of the discriminator instead of trying to maximize the output of the discriminator? So you take the true data samples, pass them through a few layers of your discriminator, get some feature vector. You pass the generated samples as well, and then you just say that if my generator had generated good samples, then the features must be close to the true data points. And as long as your discriminator keeps improving over time, the features it learns are good. So this is likely to be a good learning signal for the generator. So this was one of the tricks proposed. This is an objective function for the generator now instead of the max-min objective.
Wait, how do you get that?
Sorry? Yeah, so the discriminator trains as a binary classifier still, but so it's learning some features, and the generator is just trying to.
You just take a random layer of the discriminator?
Yeah, yeah. Historical averaging. So this is somewhat motivated from game theory. They do some experiments, but I'm not going to cover that. But what they're trying to say is, if you can break the symmetry by trying to average your parameters over time, so something like exponential moving average, and this stabilizes the training somewhat. The third thing is called mini-batch discrimination. This is a really cool idea where you're trying to make the discriminator aware of other samples in the batch. So let's say that you get a feature vector for every input, and there is a matrix that takes, so let's say that there is a tensor A cross B cross C that's a parameter that takes in the input f of xi and gets you a matrix mi. This is some B cross C matrix. Now you could take 2 different samples xi and xj, and for every row in this matrix you calculate this exponential of the L1 norm, and then you compute features that sum over all the rows. So you can basically get sum over all the other inputs in your mini batch, and for every single row, and you get a new set of features. Should have as many values as the number of rows in this tensor, and you append it to your original f of xi features and pass it through the next layer of the discriminator. And if you keep doing this, it kind of helps you to address the mode collapse problem, because it measures if this tensor will somewhat be trying to tell the discriminator that it's not just the single sample being good that I care about, but it's also that I want to make sure that the batch doesn't contain all of the same. So I need some way to discern across the samples in my mini batch, and this kind of some distance measure between samples helps you do that. It's a heuristic fix for mode collapse, but very interesting at the time, kind of an interesting architectural choice. So that's why it's called mini-batch discrimination. The other trick is called one-sided label smoothing. This is somewhat inspired from adversarial examples and other work from Hinton earlier on using smooth labels. So for binary classification, you don't have to use 0 and 1 as your targets. Cross entropy can deal with any kind of distribution. So instead of having this as the default discriminator cost, you could have the target value for the the data variables as 0.9, 0.1 instead of 1 and 0. So this way you're sort of smoothing your discriminator objective. And it's only done on one side. So it's only done for the data samples and not for the generated samples. They have an explanation for this, but I personally didn't find it very correct, so I'm not going to present it here. Yeah. Yeah.
Could you go back to the mini-batch smoothing, or the mini-batch slide?
Oh, yeah.
Mini-batch discrimination, yes.
Yeah.
How do you, so this, you just take L1 distance, like so
Oh, yeah.
it's like an image, right? Or
Yeah, so you have an image. It becomes a vector. And after this tensor operates on it, you get a matrix, right? And you get this matrix for every single input in your batch. Now, for each of those inputs, you take one row of this matrix and calculate this distance, right? So B is a row in the matrix, and I and J are samples from your batch. And you take this distance measure and call this CB, and you sum it over all the samples in your mini batch. So for every single xi, you're summing CB of xi, xj for all the other j's. So it basically measures how similar xi is to the other samples in the mini batch. And you do this for every row in the matrix and calculate all of these values and figure out a new feature vector, append it to f of xi, and pass it up to your discriminator.
What's your T?
also, I see.
T is a parameter that's part of your neural net. It's a tensor that projects the feature vector to a 2D matrix.
So O of X, I is supposed to be an additional feature that tells
Yeah,
you about the
yeah.
difference between
Difference between
I and everything else.
xi and everything else for that particular row of the matrix, and you do it for every row.
And you give that to the discriminator?
Yeah, in addition to f of xi.
I mean, don't we want the discriminator to have as little information as possible? Like, the discriminator becoming too good is the worst case scenario, right, that we're trying
Mhm.
to avoid.
Yeah,
Passing extra information to the discriminator intuitively, it seems, I don't know, like misdirection.
yeah. So the best way of understanding this is this worked. So people come up with explanations after it worked. So yeah. So but there is a reason for this, which I find pretty nice. Is it's not about weakening or strengthening the discriminator here, but informing the discriminator about the other samples in the batch, and hoping that it would help address mode collapse, because mode collapse means that you have all the samples in your batch are going to look pretty similar. So yeah.
Why does, okay, yeah, I don't know, it just seems like it's weird to put this into the discriminator when you could maybe like put a penalty on the generated samples and make them far apart, and add that as like an extra term to your generator loss function.
Oh, I see. So you want to like use the feature vectors of the generated samples
Yeah.
and figure out a new distance function on that, or some kind of geometric structure on that.
Yeah.
Yeah, you can try that idea. If it works, you can write another paper.
My question was answered.
So I think like it's hard to know which trick played a big role in the improved GAN paper, because there were lots of them.
Until they did all the tricks.
Yeah, and also yeah, these are very smart people, so they must have tried all the things you're talking about.
But there's no sense of like incremental improvement with the addition of each one of these tricks, right? Like it just doesn't work, and then
So it's not like it wasn't working. It's just that you want to make it more stable, easier to like train. DC GAN was working, but super brittle, right? So these things kind of help. So let's see. Another thing they talk about is virtual batch norm. This idea is not just specific to GANs, but it's adopted in other places as well. But so if you just use regular batch norm, it turns out that the samples are very related to each other. These are the kind of samples you get. I took this figure from Ian Goodfellow's tutorial, and the way they address this is you can have a reference batch that's composed of like fixed samples you fixed before the training, and you use that to compute all the normalization statistics and not your current mini batch. But this could overfit to the reference batch. So what they do is for every single sample, you take that particular sample and the reference batch and compute the normalization. And they call this is reference batch normalization, and this is virtual batch normalization. So and that helps address the this issue over here, that you get all kinds of similar samples. So let's see. The semi-supervised learning part was also pretty smart. Let's say you had labels instead of just unconditional samples, and you want to augment the discriminator with the label information. One way of doing that is to convert the discriminator to performing a k+1 way classification task, where you have k labels in your data set and one extra label that just says that the sample is from the generator. So k labels saying true samples from the and particular class from your real data distribution, and one label for saying it's a generated distribution. And you can split the cost into the supervised learning cost here and the unsupervised learning cost here for the discriminator. And so that you can interpret this as a model performing semi-supervised learning using GANs. Yeah.
don't you want your generated samples to sometimes fall into one of the k classes?
Yeah, so you don't know that, right? You don't know what class a generated sample is. But you have a data set containing labels, but you still want an unconditional model. So you want to still use it as part of your discriminator objective. Yeah.
So do we not then need to like warm up the discriminator by like first getting it to be able to make some distinction between the classes of the real data set? Because if we like just start throwing in generated samples, it seems like this is a much harder problem for the discriminator to solve. Like we stacked on the problem of classifying. Like basically, the discriminator has to first learn how to do C-bar 10, and then learn.
You mean pre-train the discriminator?
Yeah.
Okay. Yeah, I don't know. Maybe it's good. Yeah, I don't know how they actually implemented this, so hard for me to say anything.
What's the label for image?
Sorry?
Do they have labels that you use?
Yeah, so if you have a label data set,
Okay.
or if you say have a data set with like few labels, not too many, how do you still exploit those bits to like, augment your GAN training, make it better? Yeah. So finally, they proposed a new metric for evaluating GANs. So this is called the inception score. It's very popular, used in every GAN paper nowadays. So what they do is, the rationale for this is like, if your generator is good, I should be able to take the samples it generates, pass it through a pre-trained classifier like an inception network, and the output distribution, the output labels that it produces, compared with a prior on my labels, if I take the KL of this and average it over all the samples that the generator is generating, this should be pretty high. So let's split this into two parts. So if you had a good generator, it should generate an image with recognizable objects in it. So that means if you pass that image through a classifier, the entropy of the labels should be low, because you should be able to say which object it was. So that is one part that guarantees that this will definitely ensure you produce good samples. The other part is averaging over all the generated samples. Now, if you average over all the generated samples, so this is basically expectation over P of y given G of z, the KL of P of y given G of z, and P of y averaged over the generative distribution. And that you want it to be as diverse as possible to make sure that it matches some kind of a close to uniform prior on the labels. So when you average this over the entire data set, you should be able to see almost all the labels present in your data distribution. So it captures both the diversity aspect of it as well as the sample quality aspect of it. And also they did some Turk experiments and showed that it correlates well with human judgments. So that's why people use it.
How do you get labels on your generated data?
Oh yeah, so this only applies if you have a data set where there are actually labels, but you learn a GAN or without the labels, and you try to see how well it correlates.
But how do you get Py of x if x is generated?
Yeah, so you pass it through a pre-trained classifier,
Oh, okay.
like Inception,
Gotcha.
or you could use Inception.
Oh, that's, okay, that's
Yeah.
why it's called
Yeah, that's why it's called Inception score. Yes. Right.
Wait, so can you explain what the Py term is? Or like how you get that?
So the output of the Inception pre-trained classifier is a softmax over logits.
Wait, isn't that Py given x?
Yeah.
Oh, sorry, the other.
P of y? Oh, that is just based on, you could have a uniform prior, or you could, if you're having a data set where you already have labels, you could compute frequency-based estimator for the prior. Yeah. So in practice, I don't know what's done. Yeah. But it has to be reasonably uniform so that it helps you capture diversity. So the improved training of GANs produced some very interesting samples, but like these kind of dogs, like it couldn't get the orientation and pose, but it produces good textures, and it produces really good samples on CFAR. So it was a good improvement on top of DC GAN. Let's see, what's the time? Yeah, maybe we can do Wasserstein before closing. Cool. So so far we've seen KL and JSD as divergence measures. Another divergence measure or distance measure that kind of inspired from optimal transport theory is the Earth mover distance, and it's defined in this following way. PR is real, PG is generated. So it's the infimum over all joint distributions. So the property of gamma is that the marginals of gamma should be PR and PG. So any such joint distribution with its marginal being the two distributions under consideration for the distance, searching over them of this particular term, which is expectation of x and y sampled from the joint, the distance between x and y. So it's called the Earth movers because you can interpret gamma of xy as the amount of mass to be moved, probability mass, amount of mass to be moved, and x minus y as the distance. So you're trying to move points from one distribution to another distribution with minimal effort as possible. So that's why there's the optimal transport connection. And the goal of these original authors in this paper was to somehow make a GAN try to approximately optimize the Earth mover distance as the objective for the generator. So if the generator tried to adjust PG such that it always tried to minimize the Earth mover distance. Yeah.
How do you even compute that
good question. That's what we're going to talk about. Yeah. Yeah. So the question was, how do we compute this? You can't, and you need approximate ways to do it. And let's see how to do it. So this is intractable, and a bunch of some math by Kantor-Rovich, Rubinstein. They came up with this duality, dual form of this objective, and converted this search over joint distributions to a search over one Lipschitz functions. So this notation is just basically one Lipschitz, search over all one Lipschitz functions. So Lipschitz is basically the fact that the slope of the function should be less than that particular constant. So expectation of x coming from PR f of x minus expectation of x coming from PG f of x. So that becomes your objective now. This looks very much like a GAN objective, where f is like the for the GAN it turned out f is the log d of x, where d is the discriminator. But here f is some function that you're searching over, and yeah. So you made this definition somewhat tractable. It's still not tractable. I hope you all know what Lipschitz is. You don't know Lipschitz? Okay. Okay. So let's see. If you have a function f that maps from x, the largest, the minimum constant beyond which you can guarantee this inequality for every pair of x1 and x2, if there exists such a constant m, then such a function is said to be m Lipschitz. So this is the idea, and this is defined for the metric L2 distance, but you can define it for any other distance function in the domain and the target space. So it's a generic notion of slope. So you're just trying to make sure that you're searching over smooth functions. That's a layman way of thinking about it. You're just trying to make sure that the critique or the discriminator is somewhat smooth. Is this what?
Is this kind of like the derivative is bounded, basically?
Yeah.
It works on non-differentiable functions, but what if it's differentiable is identical to saying that a derivative is bounded?
Yeah. So you just need to be uniformly continuous for this definition. Yeah. All right. So Wasserstein GAN, proposed by Arjavsky and others. So they try to use this dual form and somehow figure out how to search over this particular term. So one obvious observation they made is that this thing is linear in F. This particular thing is a linear expectation in F. So you can search over k Lipschitz functions because it's just going to be a scaled version of it. And you just get the k times the Wasserstein distance if you do that. So yeah. Oh, actually, I defined Lipschitz here. Anyway. So you basically convert this to a k Lipschitz search, and now what they say is if you parameterize functions f with some parameter w belonging to some class of parameters capital W, you can guarantee that this is going to be lesser than this as long as all of fw are Lipschitz, k Lipschitz. So you're basically saying if I come up with some subclass of functions which are guaranteed to be Lipschitz, and I just search over them, then I am searching over a subset of all possible k Lipschitz functions, and therefore I'm guaranteed to be like less than the Wasserstein distance, the scale version of the Wasserstein distance. And how do they do it? What kind of FW do they use? They use neural nets. So if you use a neural net and you still want to make it Lipschitz, this is the way you would do it. This particular line number 7. It's a very terrible way of doing it. In fact, they call it terrible themselves. But you can intuitively understand it, right? Because every layer is computing some linear function and multiplied by an activation function. Activation functions like ReLU have the Lipschitz constant to be 1. So you just want to bound the linear part. And if you clamp the weights, you're intuitively adjusting or bounding the Lipschitz constant of that particular transformation. So it is not a very unreasonable thing, but in practice, it's kind of surprising that it even worked. The rest of the part is just regular GAN-like training. So you optimize the critique for a while with this particular objective, where xi is the data points, and these are the generators. Note that here now it becomes like you just increase the value of the critique for data points, decrease it for the generator, so there is no classification task. So that's why they don't call it generator anymore. They call it a critique, which is kind of similar to how you do it in reinforcement learning, where critique just tries to estimate returns for high value return, low value return. So and you take gradient ascent steps on this objective, and after a while you take a bunch of noise vectors and try to take in the opposite direction. You try to minimize this FW function for the generated samples. So it's very similar to GAN, except that you got rid of all the logs, you got rid of the classification task for the discriminator. There is no such zero-sum version where we had all these terrible issues. And you're approximately making sure that the discriminator is Lipschitz by clamping all the weights. Yeah.
So the weight clamping kind of sounds like a pseudo-regularization.
Yeah.
Because
Yeah.
exploding.
It's not a regularizer.
Well,
Like you're not taking gradient descent on it.
Yeah, not
Yeah.
regularization, but like it kind of limits like certain paths.
It's an adjustment to make sure that you're not computing functions that you shouldn't be having in the discriminator. Yeah.
I guess what I was trying to say is maybe that like this might also help with like the instability.
It leads to stability.
Or I guess I'm just thinking because maybe like the
Yeah.
weights won't like
Yeah.
go crazy.
So we'll see what it does. I guess you expected it by now, but if you had this original GAN discriminator, which is a classifier, you saw that the gradients were 0. So the vanishing gradients in the regular GAN. This is real, this is fake. The classifier succeeds so easily. Then you don't get any this gradient for these points to move over here. But if you have a critique like this that just is, it just tries to clearly distinguish from real and fake, you can adjust the value of this critique. You can move these points to this place. So you get a non-zero gradient. The gradient is linear here, which is really cool. So you can adjust the samples. Another thing they point out is that the Wasserstein estimate is correlated with the perceptual quality on the LSEN data set. I actually don't know how they computed the JST estimate because it doesn't seem like it's possible, but I'm just producing the figure here. It was there in the paper. It was not really explained, but you can focus on this figure where if you use the Wasserstein estimate that your critique gives you, you can see that it correlates reasonably well. Starting of the training, you just have noise, and then you get good-looking bedrooms at the end. And the samples produced are on par with DC GAN. As if you use the same architecture, you just take DC GAN, run it, take WGAN with the same architecture, run it, you get similar-looking samples. Top is WGAN, bottom is DC GAN. Crucial insight is you don't need batch norm for WGAN. DC GAN will break if you remove batch norm. WGAN wouldn't. And DC GAN would have mode collapse if you have an feed-forward architecture. WGAN wouldn't have a mode collapse. So the point that they are trying to make in all this is WGAN is robust to architecture choices, whereas DC GAN is not. And this is probably because of the removing all the classifier notion of GAN. So this is the departure from standard GAN. You had a classifier, now it got converted to a critique. You're searching over a particular family of discriminators, Lipschitz discriminators. This turns out to be more robust to hyperparameters, architecture choices. So, and again, they point out clearly that weight clamping is a terrible idea to enforce Lipschitzness. But we'll see how there are better versions of WGAN. So we'll see that next week, how to have better versions of Lipschitzness. Cool, thank you.